Here. Feeling better today? About the same.
Okay.
All right, let me begin with a word of prayer here. I'll get into it. Dear Lord Jesus, we thank you for this time we have to meet and study your creation. Just thank you for these students. Just ask you just bless this class. Help us to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. So, there's been a few things that have escaped my attention. So here's a little one. Example 1. Let, f be real. So let f equal to the real part of f. In other words, and f be an element of the holomorphic functions on D, a domain. So what was a domain? What was a domain? Don't all speak at once. A open connected set. Open connected set was a domain. So f equals to the real part of f is tantamount to saying what? F equals to u plus iv with v equals to 0. So if it's holomorphic on this domain, what does that tell us? It tells us Cauchy-Riemann equations hold true, right? So we have ux equals to vy and uy equals to minus vx, right? But those are 0. So this tells me that the gradient of u is equal to 0, right? Which tells me that u is constant, right? So then what? What can I say? Oh, well, that tells me u is constant. So that's the point. All right, so thus u is constant on D. Shouldn't it be u are constant? I need another marker to throw. I'll have to settle for an eraser. I'm gonna bring weaponry next time. I have various Nerf guns in my office. I can bring them to class if need be. All right, so that's that. So you have a homework problem which is like the same stupid thing, except instead of having and by the way, if u is constant, then the whole function's constant, right? So then, which implies that f is constant on D. Which means that, if you allow me to summarize this, it's okay. It essentially means that there aren't really any interesting real-valued functions which are holomorphic. And in your homework you find out there aren't any really interesting imaginary functions which are holomorphic, right? So for like a holomorphic function to be interesting in some sense, it has to be both real and imaginary, right? It's a package deal. So there's that. So next up, I'm supposed to talk to you guys about one of the other things I missed was the power rule, right? So example 2. All right. So we can look at let's say L of z equals to the natural log of the modulus of z plus I times, let's say, arg alpha of z, all right? So this is, the logarithm, and I'm missing like angle alpha, right? There's a jump in the angle. We have to delete that in order to have a continuous assignment of angle, because we can't continuously assign the angle all the way around, because otherwise we jump by 2 pi. And but on the flip side of things, we also know that if we want to look at a holomorphic function, well, holomorphic, or complex differentiable if it will, implies continuous, right? So if we want to deal with differentiable in the complex sense functions, we can't afford that discontinuity, right? So we have to like make a cut. This is called an example of a branch cut. that specializes the domain in such a way that we get that continuity of the resulting. And this is an example of a logarithm, right? This is a particular branch cut of the logarithm. Now, with this, we can likewise define a branch of z to the complex power, right? So z to the complex power, if you don't put the stipulation of choosing a branch, it's a set of values, right? You guys have had like a kabillion homework problems about this, right? Annoyingly, we have a set of values for a complex power. But if we choose a branch, then that annoying lack of specificity vanishes it just gives you this formula, right? By definition, it's the exponential of c times, well, L of z, right? Now this would be for z an element of the complex plane with the alpha ray deleted, which my notation is that. All right? And I hope you don't make, you guys, do you want me to invent yet another notation? You don't, right? So let us understand that in this context, I am thinking of arg alpha with alpha deleted as well. So like it's defined on the interval from alpha to alpha plus 2 pi, neither of them included in the interest of not violating the continuity that I'm worried about, all right? Okay, so that backdrop in mind, we can differentiate this thing, right? And so here's how it goes. By the way, rats. We'll come back to this in just a second, but, you know, theorem d dz of L of z equals to 1 over z. So we talked about that a little bit last time, but I'll circle back and talk about it again here in a second. So if we know that, let's suppose we know that, all right? What happens, how do we differentiate z to the power c? How does that work out? d dz of z to the power c with respect to this branch. I've got the derivative with respect to z of the exponential, and that's the complex exponential, of c times L of z. So how's that go? Well, we know how to differentiate the complex exponential, and this is a composite function, so we use the chain rule. And so what do we got? We got exponential of c times L of z. Now c is a complex constant, but a constant nonetheless. So we get, I'll just write it out here, d dz of c L of z, right? But the constant pulls out, and we just have the derivative of L of z, which is what? So we've got 1 over z times, well, there's a c here, and then exponential. I move the constant out front, if you guys don't mind. But what is that? Yep.
It looks a lot like a real number. You take the derivative of a, like, let's say a real number a to the x.
Oh no, it's not that, because here the base is the variable. That would be a different thing. Yep.
It looks similar to when you put a number to a complex power, the formula for that.
Yes, Jeff. Are you messing with me?
No, I wasn't.
Okay.
Oh, okay, I see.
I mean, oh, but yes.
Never mind.
No, that is actually a very good comment. That is what we're doing. Not wrong, not wrong. But like, so here. This is z, 1 over z, right? Where's minus 1 in this picture? Minus 1 is over here, right? All right, so 1 over z is z to the minus 1. And in terms of this notation right now, that would be exponential of minus L of z. Now, this begs a question, right? It begs the question is that the same z inverse as this as is that? Because this is the exponential of minus the logarithm, right? So technically there's like a little homework exercise to do here to prove that this really is indeed 1 over z. But Anyway, that could be done. I'm not going to belabor that. The point is that this is true, and I think that would make sense because, well, let me not belabor this. So the point is we can make this calculation. So this we can rewrite as c times the exponential of minus log z, right? And then what happens? We've got c times exponential of what? See that? C minus 1 log z, which is then by definition z, well, by definition it is c z to the c minus 1 for the branch we're looking at. This should not be surprising because this is the power rule. So the power rule holds for complex powers subject that we, are on a branch, all right? So this breaks down if, for example, my z is, we're good. If my z happened to be along the alpha ray, then I'd be in trouble, right? I couldn't do that. But then if my z is along the alpha ray, then by golly, I shouldn't be using this branch to analyze the problem, right? So, any questions? All right. Admittedly, there's a small gap here, like being sure that this is reasonable, all right? So, so let me remind you, inverse function theorem, right? So we have theorem if f is holomorphic on D with f prime of z naught not equal to 0, then there exists f inverse defined near f of z naught. And f inverse would be holomorphic at f of z naught, in the sense that so what I'm saying is that if you have a function and its derivative is non-zero, that means that you can invert the function, all right? And the inverse of the function is in fact complex differentiable, all right? So the problem I had at the end of your last mission, mission 2, basically was this. I had basically what I gave you was w equals e to the z, right? And I had you solve for z. And when you solve for z, what you should have got is what? So this, so if I set this and solve for z, that could be z is equal to, well, the log of w. Now, of course, here, I'm supposing that w is, we have the real part of w greater than 0. If the real part of w is greater than 0, just to make, for the sake of specificity, that was the problem in your homework. And in that context, there's a formula for the logarithm. Namely, this is natural log the modulus of w plus I times actually inverse tangent of, curses. Natural log of u squared plus v squared plus I times inverse tangent of v over u, right? So that arrow was just algebraic for you guys, right? Fine. In the homework, that was just algebraic. Now, the inverse function theorem, so if we look at, f of z equals to e to the z, then, f is, it's holomorphic where? It's holomorphic on all of d, right? It's everywhere the Cauchy-Riemann equations hold. What's an example of an entire function? Where is its derivative non-zero? Right, yeah, exactly. F prime of z is equal to e to the z, right? Which, lest we forget, is e to the x times e to the iy, which is not equal to 0 everywhere. Because for it to be 0, it would require for sine and cosine to both simultaneously be 0, which is an impossibility. And of course, the real exponential, e to the x, is never 0. Now, okay, so the derivative is non-zero everywhere. Does that mean we can find a global inverse? Yeah, no. So, and the reason is that the inverse function theorem is only a theorem for a local inverse. And we can only invert the exponential for a restriction of the domain on which it's 1 to 1. So, in other words, you have to figure out, you know, where is the exponential 1 to 1? What's the deal? Well, if you think about that, e to the z1, right, equals e to the z2 implies what? Implies that the real part of z1 is equal to the real part of z2, right? And it says that the imaginary part of z1 yeah, very good. Yeah, plus 2 pi k for some k in the integers, right?
Or essentially just 2 pi c.
Right. So, in order to have 1 to 1, we have to limit the imaginary part of y so that we can only get one value in that infinity of choices.
Essentially choosing that branch cut.
Right.
Is the 2 pi k part.
Yeah, choosing a branch cut, what that does then is, choosing the branch cut is choosing a particular value for the logarithm, which for the exponential corresponds to limiting the domain to a particular horizontal strip, for which that branch cut is the inverse, the local inverse of the exponential for. So the standard logarithm, now your homework problem, I artificially reduced the discussion to the positive reals to make it easier for you guys. But of course the principal logarithm is actually defined not for just this, but for the slit complex plane with the negative real axis removed. So how do I know the derivative of the exponential is 1 over z? All right, excuse me, the logarithm. Well, here's the calculation. We have that w equals to, well, excuse me, let me say it this way. We let L, let L of z, be branch of little log z, right? Meaning, what's that mean? That means that the exponential of the L of z is equal to what again? It's equal to z again, right? It is an inverse function for the exponential suitably restricted. Now, so let's see here. I need to come up with like a, let me just, this is the usual. So we do this in calculus 1 at the end, this calculation I'm about to do. We do it in calculus 1 to calculate the inverse of inverse sine, the inverse of inverse tangent. This is the inverse derivative calculation. How does it go? Well, usually we let a letter equal to the inverse that we're interested in. All right, so in this case, I'm interested in the logarithm. So I said w equal to logarithm of z. Then what I do is I operate by the function I already know the derivative of, which in this case is the exponential. So I take e to the w of each side. What is e to the L of z? Well, by construction, that's z, right? Now keep in mind, the inverse function theorem tells me that for this z I'm considering, there exists a differentiable function, L of z. Like L of z is differentiable. That is given, the existence of the differentiability in the complex sense is given to us by the inverse function theorem, which means that I am well within my rights to differentiate this equation, right? So I differentiate it, and I get e to the w, dw dz, is equal to, well, dz dz, also known as 1. Then I solve for dw dz, which is what I'm after here. And that gives me 1 over e to the w, also known as 1 over z. So lo and behold, we have proved that, within the appropriate branch cut, d dz of the log of z is equal to 1 over z. Anyways, I wanted to go back through that because it's kind of an important idea in here. It's an important idea in Calculus 1, right? How do you calculate the derivative of inverse functions? Well, this is how. Now, how do you find the formula for inverse functions? Well, that's another matter entirely, right? That was the last problem in mission 2. I showed you actually how to do it. Well, I didn't show you. I made you do it, but you know, maybe I didn't. I tried to make you do it. I guess you might not have done it, right? Any questions? All right, so moving on here. We should talk about what it means for a mapping to be conformal. So what is a conformal map? Do you guys know? Anybody? Oh, you got me.
Something that preserves angles between like vectors.
Something that preserves angles between vectors would be exactly correct. That's exactly what it is. A conformal map is a mapping which preserves angles between vectors. Let me make that a little bit more precise in the sense of how to measure that. What do I mean by angles? How do you get a vector anyway, right? So we're thinking about f as a complex mapping. And so, you know, f goes between one, we just visualize the complex plane 2 times, right? So we got the z-plane, which we have z equals x plus iy. And over here we got the w-plane, where we usually use u equals, w equals u plus iv, all right? The domain, the range. And so we can take a path here, like these, and we can pick a point, like that. And then over here, it will give you another path over here. So this path over here would be something like f composed with gamma 1. All right, so this is gamma 1. To be more specific, you could like, gamma of t could be e to the it. That would be a unit circle. Gamma of t equals e to the it would be a unit circle. F of e to the it would be the image of the unit circle under the map. Now, excuse me, then you have another path, like these. Let's call it gamma 2, right? And that would give you another path over here, f composed with gamma 2. So we can study the map, we can study paths before, and then the image of the paths under the mapping. All right? So when we say it's preserving the angles, so the natural thing to look at is, you know, we have a vector, like a tangent vector here. Let me see here. So I've got so the tangent vector to v1, let me call it v1. And then over here, this guy, let's say the tangent vector, I'll put a bar on it, to the 1, like that. And the tangent vector to gamma 2 at the point we're interested in here, maybe v2. And then over here would be the tangent vector to the other guy over here, v2 bar. So to be conformal would mean that if we take 2 intersecting paths which have, you know, vectors that point tangent at the point of their intersection, we should like for the angle before at the point of intersection to be the same as the angle afterwards. So in short, like this angle right here, this angle right here, let's say theta, should be equal to this angle over here, which I might call theta bar, sticking with my notational scheme. Now here's the thing. What's the formula for like the tangent vector? How do you get it? So 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 what we do is just to keep things simple, We'll suppose that gamma 1 of 0 is equal to gamma 2 of 0. That's the point of intersection. All right? And certainly you can choose paths to be parameterized in this way, right? You can always redefine your parameter to make 0 at the point you're interested in, if it's not already. So that's not a big imposition. Now over here, so like V1 bar would be f composed with gamma 1 prime of 0. And over here, like V1 would be gamma 1 prime of 0. V2 would be gamma 2 prime of 0. That would be the tangent to those paths. Right? So like V2 bar is, guess what? V bar 2 is f composed with gamma 2 prime of 0. Now at the end of the last chapter, I derived a chain rule for like a complex function evaluated at a path. What was the chain rule? Do you guys remember? So how does it work? If we take d dz of f of gamma of t, how's that work out? So here I'm assuming that f is a complex differentiable map and that gamma is like a smooth function of time. It's a parameterization of a path on the complex plane. So the chain rule I worked out there is just this. It's df dz evaluated at the path times, well, d gamma dt. Or in the other notation, in the prime notation, this is f prime of gamma of t times gamma prime of t. So what happens when you look at t equals to 0? So if we look at t equals to 0, like just use the chain rule up here, right? This is what? This is equal to f prime of gamma 1 of 0 times gamma 1 prime of 0. And this is equal to f prime of gamma 2 of 0 times gamma 2 prime of 0. Right? Let me just, you notice that these are equal, like let me underline it in red. Notice that since we are assuming the paths intersect when the parameter is 0, like this is the same point here and here. Those are equal, right? So for the sake of discussion, let's just point out that this is a complex number. Let's call it c. Right? So what do we have? Let me write the equations that we have. We have v bar 1 is equal to c times, well, v1. And v bar 2 is equal to c times v2. Now I have a proof in the notes, which is like a half a page, and it's glorious, but we don't really need that. If you recall back to the start of this class, what did we talk about? Like day 1, polar representation of complex numbers, right? What does it mean to multiply by a complex number? What is it? It's a rotation and a dilation, right? So think about this problem geometrically. If you take vectors v1 and v2, right? And you multiply them both by the same constant, what happens? You're rotating them the same way. So the angle between v1 and v2 doesn't change. Therefore, a complex map is necessarily conformal. What is the gap in my argument? When is a complex map not conformal?
It's not differentiable.
Oh, but if I'm assuming that it's holomorphic, so let's see, theorem f, an element of holomorphic functions on D is conformal on D provided fill in the blank. Or maybe instead of conformal on D, let's say conformal at Z naught. Because conformality is really not it is a local property. It is concerning vectors that are based at a particular point and what happens to those vectors as they're mapped from the domain to the range, right? So provided what?
V1 bar and V2 bar within the given angle range?
Nope. Nope. There's no. It's not. None of that log branch junk we were looking at matters here, yet. I don't. They might not matter actually at all, for this. I mean, these could have been any which way. It wouldn't have changed anything. I said that they both are rotated by the same angle, right? Anybody see the problem yet? Yeah?
If we multiply by 0, wouldn't it have no angle?
There we go. It's 0. We need that f prime of z naught is not equal to 0. That's it. That's the thing. That's where it breaks down. If we multiply by 0, all bets are off. Right? What angle, when you rotate by 0, what's your angle you're rotating by? It just collapses all the things to 0. Now, do you understand what this means? I mean, I think the application of what we were doing to Laplace's equation last time is like extremely surprising. That every real and every imaginary component of a holomorphic function is necessarily a solution to Laplace's equation. That's very beautiful. It's very beautiful. But this, in some sense, is even more beautiful because of what it means geometrically. Let me try to explain. So, if we think about the W plane for a second, right? And if you think about F equals to U plus IV, right? And if we think about U of Z equals to a constant, right? Say C. And if we think about V of Z equals to a say C2, C1. Do you understand what we're looking at? Like, let me make this more concrete. Let me give you an example. Let's see here. Example 4. So like, let's keep it relatively simple. Well, we like the exponential. Let's look at the exponential for a second. F of Z equals to what? E to the x cosine y plus I e to the x sine y, right? So there's your U, there's your V. So if we study the equations, well, it depends on what we want to look at, right? Like, if we're in the W plane, what do these look like? It's very silly in the W plane. How about over in the Z plane? I mean, it's a question of perspective. When I write this, right? Forget the Z. Maybe erase the Z. The Z is misleading. So we say U equals to C1, V equals to C2, right? On the other hand, over here, we can also look at U of Z equals to C1, U of Z, V of Z equals to C2. So in the Z plane, I would think of these equations as like e to the x cosine y equals to a constant, or e to the x sine of y equals to a constant. Now, honestly, guys, I have no earthly idea what that looks like. They're level curves. It's a formula with x and y set equal to a constant, right? So it defines some curve. If you want, I guess I could solve, this would be like y is equal to inverse cosine of like C1 over e to the x, right? And we could take a gander at that thing in the Desmos if you wanted to. Wanna? You're like, no, we only use Mathematica. Let's see here. I shouldn't speak ill of Mathematica. Dr. Wang has spent a long time building a vast archive of deeply interesting Mathematica things, but I think they're underused by our department at the moment, unfortunately. Now, on the other hand, this one, I could solve for like y is equal to inverse sine of c2 over e to the x, right? And then I'm like looking at these curves as graphs. Now, in contrast, this is easier. What does u equals c1 and v equals c2 look like? No, not a point. A line. U equals to c1 is like this, right? This is u equals to c1. It's a vertical line. V equals c2 is a what? Right. Well, what angle did these meet at? 90. And what are these mapped to? What are the solution sets of these equations mapped to?
The same angle.
Right? So if you take tangents to these curves, they map the tangents to those curves. That means that these must be perpendicular here. But they're wacky. I mean, who knows what they look like? Oh man, I hope this works. Well, first of all, would it actually plug in? Come on. If this goes sideways, I already have pictures in the notes, right? All right, let's try it out. So we want y equal to, is it just do cosine inverse? Oops, I don't know what that is. What do we got? A divided by e to the x. Add a slider, yes, I think I will. And then y equals inverse sine. Oh man. B divided by e to the x. Add slider, yes please. And look at that. See where they meet? That's a 90-degree angle, right? And if I change A and B, that corresponds to changing the values of C1 and C2. Watch what happens. See wherever they meet? Still right angle. Right? Assuming they meet, of course, but that's conformality. The perpendicularity of the range has to transfer back to the perpendicularity of the domain. Let me show you some more in the notes. So here, let's see, what am I looking at? Sorry, I got to find the start of this example. Oh, this is z squared. So what I'm looking at here are the level curves of the z squared function, which would be like x squared minus y squared equal to a constant, and 2xy equals to a constant. So what you're looking at there are either, I think they're both hyperbolas. So yeah. So there's some more of those. And you notice that the one place this gets messed up, where is z squared not conformal?
At z equals 0.
Z equals 0, right? That's where this pattern breaks down. Like,
There's no such thing as angle information at z equals 0.
right, yeah, z equals 0's got exactly no information at all about preservation of angle there. Precisely. Here's, let's see, what is this one? Here's a picture of the UV coordinate lines, the inverse image of the UV coordinate lines under the exponential map. This is more of what we were just looking at all at once. As you can see, it's just beautifully perpendicular like that. So if you want some kind of like graphical, if you want to like take a picture in the plane, right, and map it in such a way that the angles between things are kept the same, but then like more globally it's kind of like deformed. These are what you want, right? So like these kind of transformations, if you pass a picture through them, they're going to like maintain sort of like the local information about the picture, but globally they'll kind of smush it or squash it out or whatever. these kind of transformations are a lot of where those wacky, you know, picture transformations you might find. Oh, another thing, if you calculate the gradient of the component functions, then they're perpendicular. Like the gradient of u dot the gradient of v equals to 0 by the Cauchy-Riemann equations, which shows you that the level curves of u and v are perpendicular, assuming that the gradients are non-zero. If either the gradient of u or the gradient of v is non-zero for a holomorphic function, it's necessarily the case that the derivative is non-zero. So I'm not saying anything different. Oh, and I've run out of notes. So, any questions? So, listen, to properly understand a complex function, like you just have to get your hands dirty, generally speaking. When I have a new function and I'm trying to understand it, what I do is I look at vertical lines or horizontal lines in the domain and see what they map to. Or I might look at circles and see what they map to. And if I just study that kind of thing long enough, I can usually come to some sort of understanding of what it actually is doing. If your function is something that you already know from real calculus, a lot of times a good approach is to focus your attention on what you already know, because a general principle of things is when we build complex objects, they have to agree with the real objects in as much as they restrict to the real objects. So if I'm finding an inverse sine, for example, one of the branches for inverse sine has to agree with the standard inverse sine branch. And where is the standard inverse sine defined for? Well, minus pi over 2 to pi over 2, right? So there's got to be a branch of the inverse sine which is defined at the origin for the complex numbers. And it turns out if you just study from minus pi over 2 to pi over 2, there's like a vertical strip there that anyway, you can kind of branch out from there, pun intended, and make sense of it. But I need to go on here and talk about other things today. Certainly we can talk more about branch cuts once we have what we need is a specific question to dig into to go further in that direction. By the way, the spider, the grid and the circles, I think those were the other interesting way to do it is to look at constant x and constant y, right? Because x equal to a constant, y equals to a constant in the domain, those are also perpendicular, right? So the image of constant x or constant y in the domain has to map over to something that gives you a rectangular orthogonal coordinate grid on the other side. So for the exponential, what happens when you put in a constant? We can talk about this for a second. So this is what? E to the x, e to the iy, right? So if I look at f of t, what do I get? I get, well, e to the t, right? And if I look at f of it, what do I get? I get e to the it, right? So, in other words, z equals to t is what? Z equals to t is real, right? So it's basically just this, right? Here's z equals to t. Z equals to it is what? That's here, right? So what are those mapping to? What is this? This is, if this is equal to w, this parameterizes what? Right? So let me use some color coding here. I use color coding a lot in these kinds of things. So think about this. It's helpful to take the real line and look at it in two terms. Like there's this guy, right? From 0 out. And there's also this piece over here, right? And so when that maps, minus infinity approaches 0 but doesn't get to it, right? And then that maps out to 1, right? And then at 1, it takes over, and then that goes on, right? So basically, the real axis maps to the positive reals under the exponential. This, on the other hand, right, maps to what? Yeah, but it's worse than that, right? If t goes on both ways, it maps to the circle, that's true, but actually it does what?
It maps to like a helix version of the circle, basically.
A helix version of the circle. Well, that,
Looping back in on itself over and over again.
yeah, that, so yeah, if we could separate, so what Ben's saying is it covers the circle infinitely many times. It's wrapping around the circle infinitely many times. And if you wanted to separate that infinity of times, you'd have to imagine breaking it out into like a spiral. Yeah, the slinky. And those different parts of the slinky actually correspond to different branch cuts. But anyway, this ultimately leads to what's called a Riemann surface, but that's, Anyway, my point is, it's just that. And if this is oriented this way, this is oriented that way. And then you can look at other curves, right? Like if we did, for example, I don't know. How about over here? What if I did this line? What would this be? Z equals to what? Maybe 2 plus IT? What's that map to under the exponential?
Circle of radius 2.
Almost.
Radius e squared.
Yeah, radius e squared, which is like a poor choice on my part is what that is. So like over here. Anyway, you get the idea, I hope. And then if we were to study a grid, we would get a family of concentric circles and rays that go out from the origin. That's the picture I had up. This is the analysis which leads to it. But the thing is, you can cover, and then you can start to appreciate what's the range of the exponential from this picture. What is it? It's everything except for that. So the range of the exponential is the punctured plane. All right. Anyway, I think I've said enough about that. I should go on. So what's yet another characterization of holomorphic maps? Is there another way we can appreciate conformal, good grief, holomorphic maps, right? The Vertinger derivatives for sure. So we have those 4 definitions for like just the basic definition, right? Difference quotient, the Carathéodory viewpoint, continuously differentiable and satisfies Cauchy-Riemann, or the Vertinger, those 4 equivalent definitions of holomorphic or complex differentiable at a point in certain ones. And then we talked about harmonic, right? The harmonic criteria, that works. Given topological restrictions, like we have to have harmonic component functions. And now we see that we have to have conformal component functions in the sense that the level curves to the component functions have to be perpendicular. They're not just free to be any which way. They have to be perpendicular if the derivative is non-zero. That's incredibly restrictive, right? But there's more. And that next topic is power series. And it turns out, so I don't know if you guys know much about the history of power series. Do you know? How old are power series?
400 years?
They're old, yeah. For example, Newton, Leibniz, they did calculations with power series, right? So they've been kind of with us from the start. But there was a time when calculus, like the foundations of calculus, the epsilon delta thing you guys have seen that we did here, right? That's a modern invention. That's from Weierstrass, mid-19th century. And so the time before that, mathematics was done more informally. So like the foundations of calculus were not, the limits were very ambiguous. Really, the dx and dy's, they were almost a notation for like an arbitrary finite increment. You still see that notation used in Calculus 1 where we talk about the differential, right? This confusion between dx and a delta x. That is an homage to the original informal carelessness of the calculus. And I say carelessness, but it's no judgment on like Newton or Leibniz, because that was just how mathematics was done back then. Careful, rigorous mathematics is something that's only happened, you know, since like about the Civil War or so. You know, in the backdrop of this, calculus is the big story, right? But if you ask questions about exactly what is at the base of it, how do you define a limit? How do you carefully define a limit? Well, if you're in the time of Lagrange, you didn't have an answer to that. Like, it's just, there's people who say different things. Euler's, right, this like master work on how to do all of the algebra under the sun. Everything we done in here, Euler did. But he did it in an informal and somewhat hand-wavy way. Not that he was careless, he was merely practicing the customs of mathematics at the time. But of course Euler had a way of being careless and not make a mistake, because he was Euler. But you see, this bothered people who wanted to have a precise definition for like what a limit was. And so Lagrange made this like big prize if somebody could explain carefully what the fluxions were. Fluxions were how Newton talked about the foundations of calculus. And I forget what Leibniz did, but you know, he put this out there like a big prize. Somebody would just carefully do it, you know. I know it's boring because it's the basic thing everybody is using to actually do interesting mathematics, but how do you do it? And then like this prize stood basically. I mean, people tried it, but everything wasn't up to the, I hope I'm remembering the right French person, up to Lagrange's standards. So this led to Lagrange writing a book on calculus. And the start of Lagrange's book on calculus, which was published in like 1780-ish or something like that, it starts with, consider an arbitrary function. And then he writes the formula for it. And the formula for an arbitrary function in Lagrange's calculus is a power series. So like his abstract template on which to draw calculus is power series. And that goes an awful long way. Like many functions admit power series representations, right? But not all. But not all. There are real functions which are smooth even, can be infinitely many times differentiated, and yet they fail to have a power series representation. That would be an example of a function which is smooth but not analytic. For example, e to the minus 1 over x squared, where it's defined to be 0 at x equals to 0, and elsewhere it's defined by e to the minus 1 over x squared. You can prove that that function has derivatives of arbitrary order at every point on the real line, and yet if you calculate the Taylor series at the origin, it's straight up the 0 series, which of course does not represent e to the minus 1 over x squared, which is manifestly non-zero away from 0. So that's a relatively simple example of a function which is smooth but not analytic. Don't ask me for another. And so what I'm about to tell you is very cool, because all of that, the diabolical the other out in the real analysis doesn't happen here. If your function is holomorphic, it is necessarily analytic. Analytic means the function can be represented by the power series at the point, and the power series that you generate through Taylor's theorem reproduces the function at that point, right? So every holomorphic function is necessarily analytic. So that's one of the major results. Now, I need to tell you what power series is. Listen, so I owe you some discussion of like convergence and divergence. You're like, oh, please, I've been missing calculus too. Like, I've been missing the ratio test and the root test and the all of that. Like, please, sir, go back to that. That was my favorite part of the calculus sequence, right? Well, you guys are math majors. You might actually miss it. I don't know. Some of you are math majors. But no, I mean, like that, all of that stuff we have to come back to, and I'll do that next class, all right? Not all of it, actually. Some of that stuff's dead to us, but here it is. So definition, a power series centered at z naught with coefficients a0, a1, dot, 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 you know, in the complexes. In the complexes, of course, has form the sum n equals 0 to infinity of a sub n z minus z naught to the power n. Right. Now technically, I've put the cart before the horse because I should have defined for you what is a numerical series. Like, how do we define series in the complex numbers? But the definition is the same as the one you saw in calculus 2. A series is the limit of the sequence of partial sums when that limit exists. In such a case, we say the series converges, otherwise we say it diverges. All right? So we can get back into that next class. I don't want to burden you with all of that today. All right? I want to focus on the majors here. So this is a power series. It has this form. And just to, we just hit the high points here. Basically, we have a theorem that there exists r greater than or equal to 0, or r equals to infinity, such that the domain of, I need to give this thing a name, let me call it f of z, such that the domain of f of z above, all right, is a subset. Well, excuse me, I shouldn't say subset. It includes, well, fine, you guys don't mind if I do this, do you? Includes z in the complexes such that the modulus of z minus z naught is less than r. So what I'm saying is the domain of a power series necessarily includes a disk of convergence. Or it could be, if r equals to 0, the power series only converges what? One place, like a point, right? That could happen. So the domain has to include a disk of convergence, which is either finite or it could be infinite. It could be the whole plane. But that's it. It has to include this disk. And the more complete statement of this is that, like, the domain of a power series, it includes this like disk of convergence and possibly some points on the boundary of the disk, but that's it. Outside of the disk of convergence, it diverges. And so there's a unique r, the radius of convergence, which you can calculate for any given series. All right? So we can prove the existence of this r, and we should do that next time, okay? What's beautiful is that a power series is necessarily holomorphic on its disk of convergence. All right? Now the proof of this is typically given later in this course after we have something called Cauchy's generalized integral formula. At which case magical things happen and things get easier. We have no such technology, you see, so I've made my job much harder at the moment, because I have to prove that a power series is complex differentiable with the tools we currently have at hand, which are what? Those 4 methods. Do I want to calculate the limit? No, I don't want to do that. Do I want to calculate the Cauchy-Riemann equations? Oh no. I do not. I want no part of calculating component functions of this bad boy. No, sir. No. Vertinger calculus. I'm a little scared of that. So that might, who knows? I haven't really thought about Vertinger. Vertinger might be even easier. No, I'm going to take the approach of the theorem of Carr-Theodori. So the theorem of Carr-Theodori